Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is the final video in a series on anti-differentiation, so kind of an introduction to the final chapter in a Calc 1 course or the beginning chapter in a Calc 2 course, depending on where you take the course. And we are doing synthesis questions at this point, just things that pull together stuff from the past with our new language. For an example, the graph of a function is given below. And this function is just little f, and we want to sketch the graph of the antiderivative of this little f. Well, this little f, if we're sketching its antiderivative, that means that the derivative of capital F is that little f. So basically, we are looking at the derivative function right here. And we want to sketch its parent. We're going to climb that ladder and sketch the parent. Well, to look at this derivative function, we would say, okay, well, the derivative is 0 right there, and there, and there. So for our parent function, the derivatives would be 0 at those points, okay, at 0, 2, and 3. All right. And then we can also use the fact that we know our function little f here, which is the derivative of the function we want to draw, is negative. So between 0 and 2. So I know that our function is going to be decreasing in this interval. And our function little f is positive between 2 and 3. So I know the parent function will be increasing in this interval. And then over here from 3 onward, our function, our parent function, will be decreasing again because you're looking at the derivative of it. The derivative in this region is negative. Okay, so hopefully that makes sense. Let's see what else we can pull from this. If this function little f is actually the derivative of capital F, then we could also concern ourselves with the concavity of capital F. Remember, the concavity is to deal with the second derivative, or in other words, the derivative of this derivative. So if we take a look at the derivative of this derivative and look at the intervals of increase and decrease, that'll help us quite a bit. So notice that this function little f here, which is capital F prime, is decreasing from this to this point. So that means capital F double prime, I'll say it that way, capital F double prime is negative here, because again, capital F prime is decreasing. So capital F double prime is negative. And then I'll use green. Our function is increasing, little f is increasing here on this interval, which means the derivative of little f, which is capital F double prime, is positive. So let me write that again. Capital F double prime is positive. And then again, little f is decreasing here. Little f is capital F prime. Capital F prime is decreasing, means the derivative of capital F prime is negative on that interval. So that is capital F double prime is negative there. And then from that point forward, little f is increasing, albeit more and more slowly, but it's increasing. And so therefore capital F double prime is positive. There. That's a lot of information to write down. So what I might do is what I do when I do my graphing using calculus. I'm going to bring out a ruler and I'm just going to line up information about the derivative of capital F and the second derivative of capital F. Why not, right? So let's go ahead and line this up. I'll do it twice here. And I will eyeball the rest of it. That's not that big of a deal. So we have, this is going to be representative, a number line representative of capital F prime. And this will be a number line representative of capital F double prime. Where does F prime, which is little f, where does that become 0? At 0, at 2 and at 3. And capital F prime, which is little f here, is negative on this interval, so our function should be decreasing. It's positive on this interval, so our function should be increasing. And it's negative on this interval, so it should be decreasing. And then do the same thing. When is our second derivative? 0. It's 0 when our first derivative has tangent lines of 0, basically. Of sub-0, sorry. So at 1, at, let's see, 2.5 probably. You can kind of see it right here at 2.5 roughly. And then also at 3.5. So I'll put that right down here, maybe right about here at 3.5. We can see that f double prime is negative here, so we have concave down. It's positive there, so our curve is going to be concave up. It is negative here, so our curve will be concave down, and it's positive there, so our curve should be concave up. Now they've given us all that information. I am now going to go ahead and just clear off this messiness so that it's out of my way. I'm going to graph the function capital F on this same graph right here. They give us one extra piece of information. Because antiderivatives are something plus c, they would like to tell us what that plus c is, right? Our antiderivative is capital f of x plus c, but they're telling us f at 0 is 1. And so that means that I know where my function starts to be graphed at 0, 1. I'm going to pretend as though 0, 1 is right here. 0, 1. So that's our initial point. I know the function is going to be decreasing and concave down. And let me use a really vibrant color for this so that it really does stand out. And maybe this really ugly green. So it's going to be concave down and decreasing until I get to 1. So let's start there. Concave down and decreasing until I get to x equals 1. And then at x equals 1, it's still decreasing, but concave up. So at this point right here is an inflection point. It's concave up until, let's see, it decreases until I get to 2. So let's just do it like this. All right, perfect. That's a really good, actually, representation. And then at 2, it starts to increase. And it'll increase being concave up from 2 to 2.5. Say it looks like this. And then at 2.5, it'll switch to being concave down. It's still increasing though, until it gets to 3. And let's just pretend that at 3, it hits the x-axis. Why not? It doesn't have to, but let's just say it does. So it's concave down and increasing until you get to 3. And then at 3, it's decreasing and concave up. That's kind of weird. No, sorry, it's concave down. So decreasing and concave down until you get to 3.5. So let's just say that's right about here. There we go. And then from that point forward, it's decreasing but concave up. So it might look something like this. It's still decreasing, but it's concave up. That green ugliness is actually the graph of capital F, or a representation of the graph of capital F. It may not be exact, but it's pretty darn close. That's kind of a good synthesis problem, graphing the antiderivative based on the derivative. And you've done stuff like this before, you just haven't called it the antiderivative in the past. Now this problem is a really good problem because it's, I don't want to say easy, but it showcases something very interesting. So determine whether or not capital F, which is this 9x minus 7 to the 5th times the natural log of 3x minus 2, determine if that's an antiderivative of the given function. So if you look at this given function, that is a terrible looking function. And we're being asked, is that capital F the antiderivative? If you're thinking to yourself, I have to find the antiderivative of this function, you're going about it the wrong way. They gave us a function and they said, I think this is the antiderivative. One way you can check is by taking its derivative and seeing if it turns into little f. That is capital F prime equal to little f? That's really what we want to know. So it's much easier to take a derivative than it is to take an antiderivative. And that's the point of this example. This example illustrates why there's a whole entire course in calculus dedicated to antidifferentiation called Calc 2. It's because finding the antiderivative of this without somebody giving me a hint is really difficult. So you need some type of a hint, some type of trick or whatever. Luckily, they give us a function. They say, I think this is the antiderivative. All we have to do is take the derivative of that capital F. Well, the derivative of this capital F right here by the product rule is going to be 5 times 9x minus 7 raised to the fourth, but by the chain rule times 9, and then times the second function, natural log of 3x minus 2, plus the second part of the product rule, 9x minus 7 to the fifth times the derivative of the natural log of 3x minus 2. Well, the derivative of a natural log is 1 over its argument, but then by the chain rule times 3, derivative of the argument. And now it just looks like what they did is combine everything into a single fraction. So let me clean this up. This becomes a 45 times the quantity 9x minus 7 raised to the fourth natural log of 3x minus 2 plus 3 times the quantity 9x minus 7 raised to the fifth over 3x minus 2. Now I will multiply the numerator and denominator of this first term by 3x minus 2, and we get the following. I'll just pause the video and then rewrite it. And that's what we get. And then we'll go ahead and look up there and see if they're the same. They don't look the same yet, but it looks like they factored out a 3 and a 9x minus 7 to the fourth. Let's see if we can do that. Do these two terms, right? Let's see, here and here. Do they share a 3 and a 9x minus 7 to the fourth in common? And the answer to that is totally yes, they do. So I'll factor out a 3 and a 9x minus 7 raised to the fourth. When I do that, I'm left with a 15 times a quantity 3x minus 2 times the natural log of 3x minus 2. Plus, we factored off a 3 and then 4 powers of that 9x minus 7. So we just have a 9x minus 7. And this is all over 3x minus 2. Let's see if that is equal to little f. And you can see that it is. So therefore, yes, capital F is the antiderivative of little f. There you go. So again, great problem to showcase that given a function, finding its antiderivative can be at times impossible. Taking derivatives, not so bad. So really, if you have a choice, you'd prefer to take derivatives, but unfortunately you're heading into an area where you're going to be taking a lot of antiderivatives. And now we arrive at the very last problem of this material. And this is a problem I stumbled upon in an online homework system, and I really like it. Suppose that capital F is an antiderivative of little f. So traditional, what we are used to. But capital F bar is the antiderivative of capital F. Now to me, just because of the way my brain works, I have to draw this out and showcase to myself what this means. So they're telling me I have this little f, and if I climb up a rung, I get to the antiderivative capital F. And if I climb up another rung, I get up to capital F bar. That's really what they're saying, okay? They're also telling me that capital F at 2 is negative 7. Little f at 2 is 8. And capital F bar at 2 is 6. Now, I have not done this problem, so I've just thought it looked really cool, so I just wanted to take a look at it. What can we say about the increasing or decreasing behavior of all of these functions at x equals 2? And by the way, what can we say or what can't we say? We might not be able to say anything about it. And usually the very last, the bottom rung, you can't say a lot about because you don't have its derivative. Remember, each step down this ladder is a derivative. Well, the lowest rung, you don't really have any further information about. So you can't tell me, oh, little f is increasing or decreasing at 2. You just don't know because it's the lowest rung on this ladder. You don't have its derivative. So I'll write that part down immediately. Again, to say something about function, whether it's increasing or decreasing at a point, we would need its derivative, and we just don't have that. However, I might be able to say something about capital F at x equals 2 because I have its derivative, which is little f. They tell me little f at 2 is 8. So I happen to know that capital F must be increasing at 2. So capital F is increasing at 2. And this is again because little f at 2, which is equal to capital F prime at 2, is equal to 8. So I happen to know that. It's perfect. Great. And now, let's see, what other thing do I know? I know something about capital F bar because I have its derivative, capital F. The derivative of capital F bar at 2 is big F at 2, which is -7. So I happen to know capital F bar must be decreasing at time 2. So I'm going to write that in. Capital F bar is decreasing at 2, and this is because capital F at time 2, which is equal to capital F bar prime at 2, is equal to a -7. I think that's what it was. Yeah, that's exactly what it was. So there we go. We have some, that's the given information. We can totally do that. We can't say anything about an F again because we don't have its derivative, but at least we have that. Really fun problem. I think it's really neat. The notation they used in the online homework system was terrible. And that's why I decided to use little f, and capital F bar. I think they used little f and G and H or something like that. And I just dislike that. So that's part of, by the way, doing problems in mathematics. Rename things to where they make sense to you so you can do the problems. All right, I hope this was helpful to you, and I'll see you in the next series of videos.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.